Let me get it moving. There we go. So what we're going to be working on today and Friday and here, the rest of today and all of Friday, is thinking about how graphs of accumulation functions can be seen and how you can look at them and see how their rates of change, like what sorts of values their rates of change have, and how their rates of change are changing also. And the other way around as well. What if I'm looking at a rate of change graph? And we actually did this back as early as chapter 4, or 5 at least. If you're looking at a rate of change graph, how I can tell what's happening with the accumulation, or how I can see how that rate of change is changing in its own graph. Things like that. So we're going to be talking about going back and forth between accumulations and rates of change, visually speaking, and how to see increasing and decreasing and positive and negative of all those various things within a single graph. So I don't know if you can see these numbers. I can maybe make them larger. But over at the left, you can see, so don't worry about the slider things at the top, but suppose that this is a graph of, let me just write this on here. Ooh, remind me later. Don't need that right now. So suppose that this is a graph of f of x. This red curve is a graph of f of x. Then what we have here, this r sub f of x, you can see its values changing. And here's just x here. Now, visually it's kind of easier to see, don't worry about the y values, but just what's going on with the y values in f of x, because that's why we would do this Cartesian graph, so we can visualize what happens with the dependent variable through intervals of or all of the domain, or as x varies. So, for instance, just a simple thing that you can talk about, oh, well, as I go from left to right here, and this is just a cubic function, it's nothing fancy going on past the edge of the screen, but I can see that the y values, the dependent variable values of function f, are first negative, then they become positive, then they're negative, then they're positive. Okay. Or, what we talked about the last time we looked at this is the rate of change is positive until we get to the top of this hill, and then it's negative until we get to the bottom, and then the rate of change of f is positive again during this end portion. We've talked about that for a while also, that, well, if you're looking at a graph of accumulation, you can see increasing or decreasing sections of the graph as pertaining to whether your rate of change is positive or negative. So when f of x, let's see minus, if f of x here is increasing, then r sub f of x is what? If I know that f of x is increasing, what word could I use to say what is true about r sub f of x? Positive. All right, and likewise, if I'm talking about f of x, the accumulation function here, decreasing, then I know that the rate of change, r sub f of x, is negative, right? And we've got those individual spots on this graph where it's kind of changing over from one to the other. So for instance, if I were trying to describe where is f of x increasing, I might say from, well, wherever I can see here, negative infinity really, up through about this spot, which is maybe around -2. I'll just call it -2 for simplicity's sake. But I could say that f of x increases on this interval from negative infinity, x values negative infinity, through about -2. And I'm not going to include -2, even if that's exactly where this top of this hill is, because at -2, in that neighborhood, f of x is kind of changing over from increasing to decreasing, or in any moment containing this top of the hill. It's not really necessarily clear which is going on. So we'll just say up through, but not including the top of the hill. We're in an increasing interval. And then it decreases for a while, and then around here, I'll just call it 1 to have easy things to write. So, and also, this union symbol, if you want to talk about two separate sections and then combine them together, so say all of this combined, dump it together in a big bag. Here's where f of x is increasing. That's what this symbol is used for. So negative infinity through negative 2, and also this entirely separate section from 1 through infinity. I've got f of x increasing, which would mean then I could similarly write, instead of f of x increases on, I could say r sub f of x is positive on, and then write the exact same things. Because if f of x is increasing, then its rate of change is positive. So I could interchange those two expressions. And similarly, I could say that f of x decreases on, well, the interval in between. Oops, not of, on negative 2 through 1. So in terms of, we've talked about most of the real number line, negative infinity through infinity, except for x values at, I'm just declaring these two spots to be negative 2 and positive 1, even though they're it's kind of close. But just for looking at this, except for those two moments right around x equals negative 2 and x equals 1, other than that, I know how to describe f. Just in those two moments, when I say if x is equal to negative 2, or if x is equal to 1, or in moments where x is negative 2 or 1, if you want to think about that, because we have to talk about a moment when we're talking about a rate of change. So if I'm looking at a moment, a small moment around x equals negative 2, or around x equals positive 1, then I wouldn't really want to say that f of x is increasing or decreasing. I can talk about it as a brief pause, or I could say that the rate of change is essentially 0, meaning that f of x value is essentially paused. Let me stop this for a moment. Speaking of pause, there we go. So in these two spots, I could talk about how f of x, the y values, are essentially, they're not increasing or decreasing, but they have a brief, you can think of it kind of like a pause, or it's not increasing or decreasing, it's that turnaround. So if f of x essentially pauses, doesn't increase or decrease, but for a small moment, in moments x equals negative 2 and x equals positive 1, if I want to talk about the rate of change, so these are easy enough. F of x decreases, oh, that's r sub f is negative. F of x increases, that's, oh, r sub f of x is positive. F of x essentially pauses means that r sub f of x is essentially 0. Very close to 0, maybe a little bit positive near the one end of the moment and a little bit negative near the other end of the moment, but it's essentially 0, and the smaller a moment I make or look at around, well, I'm declaring these to be exactly negative 2 and 1, but around those top and bottom of these hills there, the closer these rate values get to this value of 0. So f of x pausing, kind of like, well, it doesn't look like it's going up anymore, and then it starts going down, or vice versa. It doesn't look like it's going down anymore, and then it starts going up. And what I mean by this is, just if we were tracking the y values, and I don't have the y values tracked over there, all I have is tracked here are the rate values. But if I have the y values tracked, you'd see them going up quickly and then up more slowly, and then you'd see a whole bunch of y values that are about the same. And if there's only a couple of places of accuracy, it might even look like it's physically paused for a moment. And then the y values would start decreasing again until they get to around here, never decreasing very quickly. But then right around here, the y values would kind of stagnate for a while. And again, if you only had a couple of decimal places of accuracy, it might even just show as the same number for a little bit. And then those y values start to increase, and then they increase more and more quickly. So let's talk about that aspect, because this is something we haven't really talked about. We've talked about the, just generally speaking, even on your last test, we had a question about a rate of change of a bird that was flying, and first its velocity was increasing slowly, and then increasing more quickly, and then decreasing, or maybe it was the height of the bird, I forget. We talked about something increasing slowly, then more quickly, because we had a small positive value, then a larger positive value for that rate. So I'm going to clear off this stuff here. And let's just look at the rate. Now, I'm going to rewrite these x's back in. These are my sliders over here, so it came out as n automatically, but this is just the x value that's shown there, and r sub f of x. So, oops, come on, there we go. So this is x equals 2.37, where the graph is right now, and r sub f of that x value, the derivative of f of x, is about 15.6. So let's look at this, just the pattern of the rate values. I'm just going to do this manually. So back to the beginning here. I can see this rate value at x equals -4 is a rate value of 34. And then if I go forward, I have a x value that's increasing. My y value of graph f of x, the y value in this function f is increasing. I can see that without doing anything tricky, but the rate value is changed from 34 to 29 to 23. Oop, and it doesn't want to do that manually for me. It wants me to do some other things. So I'm going to put it on play. Actually, let me change this to go more slowly. Let's see if it'll do that. Nope, 500. All right, so if I look at this graph here, so I know that the rate of change is near 0 at the tops and bottoms of those two hills in this f of x graph. But I can talk about just, instead of just when the rate is positive, negative, or 0, I can also talk about when the rate is increasing and when the rate is decreasing, which is not the same as f, the y values are increasing or decreasing. For instance, if I go back in this graph here, so at the beginning, rate was like 34. Just a little bit later, the rate was something slightly less positive. So that would be the rate of change decreasing. What we want to be able to answer about this, in addition to the things that we already did, where's the accumulation increasing and decreasing? We talked about that, but where's the rate of change decreasing or increasing? We could say either one. But so at the beginning of this graph, I have a rate of change that's extremely high positive number. And I know that it becomes 0 by the time I'm near x equals -2. This rate of change is essentially 0 in that area. But if the rate of change is about 0 at that point, and it's 34 where it is now, what's happening to the rate of change? Is the rate of change increasing or decreasing? Decreasing. The function values, the y values here, are increasing from negative values to positive values. But the rate of change values, the r values, are decreasing. They're going from an extremely positive, and so think about steep graph, extremely steep to less steep to less steep. So that's a rate of change that was a large positive number, becoming smaller and smaller, and then becoming essentially 0 by the time I reach the top of this curve. So I have a rate of change that's positive, less positive, less positive, less positive, slightly positive, right around 0, and you can see, all right, so maybe it's a little bit to the right of 2, but you see, okay, that looks like in this area right here, I'm changing from slightly positive to slightly negative. So this is still decreasing, though. The rate of change values are changing from positive to negative, but the rate of change is decreasing all along. It was a large positive number, becoming smaller and smaller and smaller and smaller and smaller till it gets to around 0, and then it continues to become smaller because this is going from 0 into the negatives, and then more negative and more negative and more negative, and well, there is a point at which it stops becoming more negative, or in other words, where it stops decreasing and makes a turnaround and becomes less sharply downward, less negative. If you can see, you can see this turnaround. So I was becoming from positive to 0 to negative. That's a decreasing pattern of numerical values I could associate with that, from positive to 0 to negative. And then more negative, more negative, more negative, more negative. Oh, less negative. if you can see, it starts to tilt and go the other direction. And in fact, I know that I get back to 0 again right around x equals 1. So it goes from a rate of change around 0 to something negative to something 0 again. So my rate of change is decreasing from, as far as I can see, r sub f of x, there we go, r sub f of x decreases for most of the left portion of this graph. From here, where I've got an extremely large positive number, but as I move to the right, it becomes less positive, less positive, less positive. And it keeps decreasing until somewhere around the center section here. So I'll just say negative infinity through, and I'll leave that as a blank for right now. But I know by the time I get to, for instance, around x equals 0, this is a negative rate, but it's less negative than it used to be. And then it even becomes 0. Changing from negative to 0 is an increase. So I know that my rate function, r sub f, is increasing by the time I'm around here, where this is right now, because the rate used to be much more negative. Now it's essentially 0, and in fact it's even going to become positive, and then more and more and more positive. So I know that the right end of this graph, as I continue to go outward, is my rate function increasing all the time. Meaning, if I were to continue going out this way, this slightly negative rate here, I can see by its slightly slanted downward, this tangent line, slightly negative rate turns to 0 and then positive and then more and more positive as we go to the right. So throughout this section here, I know that my rate is increasing all the time. So it's not an easy thing to pick out on a graph. Where exactly does it change over from the rate is becoming decreasing, in this case it's negative and becoming more negative, to suddenly, well, it's negative, but it's not as negative as it used to be. It's somewhere right around 0 in this graph, where you can see it changes from becoming tangent line more steeply downward to less steeply downward. So I'll say it's right around 0 that changeover happens, meaning an x value of 0. So the left half of this graph, divided at x equals 0, has the rate function always decreasing. Meaning, as I think about rate values going from left to right, I start with large positive numbers getting smaller and smaller and smaller and smaller all the way down to 0 and into the negatives. And then somewhere around here, my rate values stop getting more negative and start getting closer to 0 again, less negative. And then they get to around 0, and then they become positive. So let me show back at the beginning. We actually had demonstrations of those rate values. So here's a list of what the rate values were. It says r sub f of n right now. I'm not going to write over top of it again. But if I'm looking at this, okay, at this spot, the rate is negative, which should make sense. It's about negative 6, negative 6.3. If I go just a little bit to the right, negative 6.32, that's more negative. Negative 6.33, oh, it's kind of frozen, and my x values are increasing, but now it's, so I've got around 0, slightly negative, more negative, went to towards negative 6, negative 6.3, negative 6.32, negative 6.33, and then back to negative 6.32. So it seems like x equals, or rate equals negative 6.33 was the most negative that we got. And that happens when x is just a little bit to the left of 0. So this is actually x and r sub f of x, just using the slider here. So it's not really 0. It's about negative 0.29 to 2 positions of accuracy here. But right around this spot here is where my rate stops decreasing and then starts increasing. So just keeping in mind that a rate decreasing doesn't mean that a rate is negative. Just like f of x decreasing doesn't mean that the y values are negative. F of x decreasing just means going downhill. R sub f of x decreasing means that your rate values, if we had a graph of those, would be going downhill. But in a graph of an accumulation function, we can see the rate by the steepness of it. So the steepness was becoming more negative, and then it stops becoming negative and becomes more positive. So this graph, the whole left portion of this is r sub f of x decreasing. And the whole right portion of it, to the right of this spot here, is r sub f of x increasing. And that's not the easiest thing to keep straight in your mind, because you say increasing, you think uphill. But increasing uphill corresponds to if your accumulation, the thing you're looking at a graph of, is increasing. And this is a graph of not r sub f of x, but this is f of x, y equals f of x. This is a graph of function f. So if I'm looking for what's the pattern in what the rate is doing, I have to think of something different. So if I see a rate that's decreasing while it's positive, that would be a positive rate that's getting less and less positive. So going uphill, but going uphill more and more slowly. Or I can have a rate that's negative and decreasing, which would be going downhill and going downhill more and more negative, more and more quickly downhill. Yeah. In this polynomial function, yes. In any function, not necessarily. So yeah, this one I believe that there's not any weird. This is a simple function. If there's a lot of this is a cubic function, and I don't think there's a x squared and an x term. I think it's just x. In general, that's not necessarily the case. It just happens to be in this one. Symmetry sorts of things. But in any case, one of the things that you're going to be asked to do between now and Monday night, you have a homework assignment in iMath AS that's taking a look at some graphs of accumulation functions and talking about what's happening with the accumulation. On what intervals is it increasing? On what intervals is it decreasing? The y values, the accumulation. You'll also be asked, looking at a graph of accumulation like this, what's going on with the rate values? Are those increasing or decreasing? Or also, are they positive or negative? So a function being increasing would indicate its rate is positive. A function decreasing indicates its rate is negative. Depending on what you're looking at in a graph, you can see that different ways, because we know we've looked at rate functions before. So just keep in mind, if this was a rate of change of something, some other function as opposed to being our main accumulation, we could interpret this different ways, because then I'd say, oh, my rate's only positive between -3 and 0. Or between 0 and 2, it hits this negative patch, or my rate is negative, meaning the overall function's decreasing. So make sure when you're looking at a graph, you understand, is this a graph of a rate of change of something that I'm supposed to be describing, or is this a graph of accumulation that I'm supposed to be describing? So you'll be given information like that. But it's very important to be able to interpret these sorts of things. But when you're looking at a rate, an accumulation graph like this, if this is just our main function, I asked you about the rate of change of f, you should be able to identify in this where that rate is positive or negative, or essentially 0 is the other option. But the new part that we haven't really talked about is that rate increasing or decreasing? And on this graph, the first whole portion of this is a rate decreasing. And notice the shape of that. When this rate is decreasing, not f decreasing, not the accumulation decreasing, but the rate decreasing, because of the sequence of numbers going from high positive to lower positive, or lower positive to 0 into the negatives, you're going to have this sort of visual shape, if you're looking at a Cartesian graph, of this curved downward effect, whether it's just a portion of it, or it could be all the way up and over the top of a hill, but just anything that's kind of curved down, or if you poured water over the top of it, it would roll off. That's that decreasing rate. On the other hand, the increasing rate portion of this, where I have negatives but becoming less negative, and then 0 and then positives, we've got this curled up sort of effect as we go from left to right. Or if you imagine, if you just had this right portion, if you poured water onto it, it would collect. That sort of curved up or cup shape, whether it's a whole part of it or just, maybe just a little piece, because graphs don't have to go all the way over the tops of hills and under that. They can, you can just have something like this, or say, oh, well, this portion is curved up and this portion's curved down. Something like, it doesn't have to be so extreme as to have a whole rate of 0 in the middle of it, or a rate essentially 0 in the middle. You can have just slightly waving and talk about increasing rates of change or decreasing rates of change alongside of increasing or decreasing function values. And those don't have to correspond with one another. If you have an increasing accumulation, your rate could either be increasing or decreasing, or it could be essentially 0 for a small moment. If you have a decreasing accumulation, you could have decreasing accumulation with a rate that's either increasing or decreasing. So those are all independent of one another. So there's essentially kind of 4 mix and match varieties of what's going on with the accumulation, increasing or decreasing, and what's going on with the rate of change, increasing or decreasing. You can mix and match any pair of those that you want. But knowing one doesn't tell you anything about the other automatically. So let me clear off some of this, and maybe, there we go. There we go. Being stubborn today. All right, so just quickly to visually summarize this sort of stuff. We were talking about how the rate of change is changing, or changes in that rate of change as we move across from left to right, or as we let x vary. So if we're talking about how the rate of change is changing, or variations in the rate of change, we're actually talking about a derivative of that rate of change. And a derivative of a rate of change, or a derivative of a derivative, the phrase that we use for that is second derivative. So if you hear the word second derivative, it's just talking about the rate of change function, how that's varying throughout a graph, or how that varies as x changes. You don't have to have a graph to have these things. But as a bonus, there aren't any new derivative rules that apply to second derivatives. It's all the same derivative rules. If you're trying to find a function rule, a closed form function for a second derivative, all it is just take the derivative of the function you had that was a derivative. For instance, and this isn't really our focus of this, but if, for instance, I had f of x is, let me give you a simple one, 7x to the 4th minus 3x squared plus 16. The rate of change of that exact closed form would be 28x cubed minus 6x, and then the 16 goes away. And if I want to know the derivative of this, we're going to talk about, there's a bunch of different notations for that, but let me just, I'll mix and match here. R sub f of x prime. There. The derivative of this, it's not new derivative rules, it's just find a derivative a second time consecutively. So, oh, why did I pick hard things? Let's see, 684, I think. 84x squared minus 6. If I multiply 28 times 3, yeah. So this expression, for instance, you can say, oh, well, for most values of x, this is going to be positive, because 84x squared, when x isn't extremely close to 0, is going to be something that's larger than 6. And so this is most of the time going to be positive, just as a note. Which what that tells me about this function is, if the rate of change of this is mostly positive, then that indicates that this rate of change function is mostly increasing, except for right around 0. Now, a rate function mostly increasing doesn't tell me whether this doesn't say that this is always going uphill. That would be this, if this was always positive, this would be going uphill. So a rate function mostly increasing, though, in terms of this f of x function, would tell me that most of the time I have that curved upward, or that cup shape, except for right around x equals 0, when this part would be smaller than 6. But so I could say that this part is mostly curved up, or turning upward from left to right. And by that I mean kind of like this shape. It doesn't have to be all of that, it could be part of that, and then little wiggles of other stuff right around x equals 0. Because if x is near 0, this is going to be slightly negative. It could be as negative as -6. And then this would be slightly, if the rate of change is a little bit negative, then this rate is going to be a little bit decreasing, which would mean this would be a little bit curved down. So those are the sorts of things we're going to be working to put together. Like if you just have that sort of information, how can I reconstruct what shape my accumulation graph would have? Or, maybe looking at accumulation, how could I reconstruct what my rate function would have as some aspects? When is it 0, positive, negative, going uphill, or just being positive and going straight across? Things like that. But just a little bit of notation before we leave for the day. Let's see. So notations for second derivative, in addition to this maybe slightly messy notation up there. If you have the d over dx in front notation, a way to use that if you're talking about a second derivative is with 2's thrown in there. Notice the 2's are in two different spots. It says, like for instance, in both of those first two, in the numerator there's a squared after the d, and in the denominator there's a squared after the x. It's just a notation, but it comes from ideas of multiplication and fractions and stuff, why they're positioned the way they are. I won't get into details of that today. But the prime notation varieties, if it's a function name, f prime prime, f double prime of x, or if it's just called y equals, the second derivative is y double prime. So there's a variety of different notations, but these are all talking about the rates of change of our rate of change function, or describing how the rate of change is changing. All right, I will see you on Friday.
Is there a quiz on Friday?
Take home.